Okay, so thank you very much again for having me. It's an honor to present. Today I will talk about topological insulator materials for neuromorphic computing, a pathway to sustainable intelligence. So hopefully by the end of the presentation, everyone will understand what I mean by that. So my research actually focusing on developing new type of the materials for neuromorphic computing. Neuromorphic computing also is known as a brain-inspired computing. So we take the inspiration from the brain to create a new type, low power consumption and uh, uh, high switching processing hardware for the computations. So today I will talk about mainly five main areas. So I will start with the introduction and motivation, why we need to start searching for the new type of the architecture for uh, artificial intelligence, machine learning, for all the computation we are doing. Why is this important? Then I will go to quantum topological insulator, a new type of the material which we can use to create new type of the devices for neural processing or machine learning processing or AI processing. Then I will talk about device fabrication and design of the device itself. And I will also talk about the brain inspired function of these devices, because as we take the inspiration from the brain, neuromorphic devices is also known as brain like devices, which we can emulate short term, long term memory, plasticity, which allow us to give our device a new type of the functionality for AI processes. And finally, I will show you some application of this one, like neuromodulation or hand gesture recognition or the AI processes as well. So let me start with the motivations. Why is this a critical way in order to create a new type of the architecture? Nowadays, all of the computers which we use, like computers, laptops, phones, iPads, everything are based on von Neumann architecture. Von Neumann architecture means that the CPU and memory unit are separated from each other. Every time we want to do something, we need to fetch the data from the memory and send it to CPU. Like 20, 30 years ago, that was perfectly fine because the amount of data wasn't much. So it was pretty good architecture for that time. Till this day, we use this architecture. But the problem appears because the amount of data we are sending, editing, sending back, process increase every single day. Actually, now, right, we are living in the world of the big data. Every day, millions of terabytes are being sent, processed, analyzed, and sent back. And in order to do it efficiently, we need a powerful computation to do it. Nowadays, how we do it, every second year, the number of the transistor per chip, which allow for the computation, was increased, double in size, according to the Moore's law. And that was perfectly fine until we reach some level of how low we can go with the dimension of the transistor. As I believe right now, the limitation is, I think, 3 nanometers with the newest MacBooks, right? Of the transistor on the single chip. Let's say in the next 2, 3 years, we'll go to 2 nanometers. But the problem appears that the size of this transistor will reach the size of the atom, which will not be stable. We cannot control this. A lot of current leaks. That is why people start now thinking that we need to develop a new type of the architecture, a new type of the processing system to speed up computational processes and reduce the power consumption. Because at some point in near future, right, the amount of data will be too much to process it by our normal computers. So we need to create a new type of the architecture, which here in handy comes neuromorphic computing. Why this is so good in this aspect is because neuromorphic computing takes the inspiration from the human brain, where the memory and CPU are not separated but are collocated. Our brain actually is extremely efficient for pattern recognition, for parallel processing. It only takes like 20 watts, like a bulb in the ceiling, to process activate our brain. In the supercomputer, the energy consumption is much bigger, and that's also a problem because it is estimated by 2030, 20% of the global energy will be used by our computers, and by mid of the century, it will be 50%. So we need to come up with a new type of architecture, a new type of devices with new materials inside to reduce energy consumption and speed up the computational power of the system. That is why our research, our team is focusing on developing new type of the materials, a new type of the architecture based on brain architecture. The three main parameters which we are wanting to achieve and are actually our main objectives is to achieve low power consumption in the range of the picojoules, parallel processing, extremely important, especially for the AI and machine learning, that we are allowing our device to process multiple information at once and create a universal chip for AI application, which is very good for the decision making, for learning capabilities, right? For developing intelligent system, because right now everything has AI and it will have in the near future. So we need to make sure that the hardware we provide for this AI is efficient enough and it does not cost millions of dollars. That's also very important. So the main area, what we are doing in the neuromorphic computing is to replicate how the human brain neural system works. In doing so, as can be seen in the image, we have our neuron and synapse structure. We emulate this one by creating similar kind of device in the same structure, right? Because there is a neuron and the synapse. Our device is based on the resistive random access memory architecture. So we have a sandwich structure. We have a top and bottom electrode, which works as a presynaptic neuron and the postsynaptic neuron. And the material inside is a key aspect here. In our case, we will use topological insulator as a functional material. In this case, our functional material replaces how the synapse works. Because in the human brain, we have a lot of neurons which are connected through the synapse, a space between the neurons, which allow us to send the information through the complex neural network. In the same way, we are trying to replicate this one with a simple structure, three-layer structure, with top and bottom electrodes working as a presynaptic and postsynaptic neuron, and the synapse is where we put our novel material, topological insulator. This structure allows us, this is a single cell, to create a very efficient, ultra low power consumption device for processing unit, which I will show you in a second. What else is very important in the neuromorphic system? That we can emulate the synaptic plasticity of the human brain. We can emulate short-term memory, long-term memory. And why is this important? Is actually because some of the application for AI or for machine learning, we can create device which does not need to be connected to computer to process. We will train this device similar to like young baby, right? Because we teach the kid how to do something and then he multiple tries and he remembers this. The same does this device work without the need to be connected to computer, and that's the key point here. This device also is especially important because of the ability to biomimic the neural network to process information in parallel way with ultra low power consumption, which is extremely important nowadays. Finally, why this device is special? Because actually this device structure is not a new one. It's already 10 years old, the resistive random access memory. But the material is new, which allow us to create new functionalities. Because this type of the material, which I will tell in a minute, have special electronic capabilities, okay, which will later on will be called like surface state, which allow us to get to a fast processing capabilities and ultra low power consumptions. So the main key, the main point in our materials which we use are actually materials called topological insulator. Nowadays they are known for the name quantum topological insulator because of their fascinating electronic properties. They are working inside in the bulk of the material as a pure insulator, but outside and on the edges, as can be seen on the image with the blue background, are conductive. How we make this material conductive fully is through surface state. And those surface states are protected by time reversal symmetry, ensuring robust surface conduction even with impurities. So what that means is that our conduction is extremely robust. Nothing can interrupt this one. Another thing is that we have high surface conductivity. Okay, why? Because insulator is inside, and because of the special surface state which are on the surface and on the edges of this material, we can create high surface conductivity. The third feature of this material is spin momentum locking. So the surface state, the surface electrons, spins are locked to their momentum. So we're reducing scattering and dissipation in devices. So we're also reducing the energy needed for those devices. Because of those three main characteristics, those materials, which are called topological insulator, are a perfect fit for neuromorphic computing, for neuromorphic hardware. Why? Because we want to achieve low power consumption, high switching speed, and parallel processing. Because of those features about unique electronic properties, all of those three things are possible to get. Our research team usually we focused on two main group of topological insulator: bismuth selenide, bismuth telluride, and bismuth selenide telluride. Those three materials are actually well known, but they are used for thermoelectrics application. We are the first group which actually use them for neuromorphic computing, which get a really good result. Then we move to tin selenide, tin telluride, and tin selenide telluride group, another topological insulator, which provide us with another functionalities, which I will tell in the second. So basically, we are focusing on topological insulator, and now on we are trying antimony bismuth, antimony selenide, and combination of this as well to see how efficient our device can be. The main aspect of this material are the surface state, which allow us to create a conductive state and edges. Okay, here on the left side, there's an impedance analysis proving that the surface state exists in the materials while we increase the voltage, and how the charges, this electrical charges goes through our material, and why the energy consumption is lower is because our charges does not need to go through something, it goes through the edges as we follow the path. That's why our energy consumption is less. And actually, what we prove here as well, that if charges go through the edges of this material, we are able to achieve high switching speed, which is another benefit of our material. How we actually develop and fabricate our devices is through electrochemical deposition technique. Why we decided to go with this one? Because it's actually cost-effective method. We can reuse the same solution, as I remember correctly, like 50 or 55 times to create a perfect device. Extremely fast. Under 6 minutes, we can create an array of the devices, and we can reuse the solution. On the right side, there is an image of the SEM in the circle and the optical profiler of how the electrodes are placed on this device. So the main reason why we actually decided to go with the electrochemical deposition technique is the price and the speed, because we can create multiple device very in the good priced. Here I would like to show you guys the comparison of different synaptic neuromorphic devices with different materials, which show compared to our topological insulator. So first go